All right, here's the bell work, 3 problems, nice and easy. Boom, there we go. All right, today we're going to be learning about percent error. So that's our objective. I can find percent error. Take 30 seconds and copy that down, please. All right. So percent error, there's a formula. It's very similar to our percent change formula, actually, with a slight difference. But yeah, we have to find how far off we are, which will include a difference. But when we divide, instead of dividing by an original, again, it works the same, but it's just now we're dividing by an actual amount. So estimate how many of those M&Ms are in the jar. The amount actually is. So if you had to look at that, I just need a quick estimation. If you guys saw that, what would you guys think? All right, so our estimation is 85. Now you see there's, this one says it's about 1,984. How do we know that? I don't know. This came from a different teacher, so there's like, here you go, 1,984, okay? So how far away from the actual value was your estimate? Well, we guessed 85, so to figure that out, we got to do some subtraction here, right? We say there was 1,984 of those, and we're going to subtract the 85 that there was, which would make 1,899. That's how far off we were in our estimation, okay? Now that's called the absolute error. I don't think we're ever like quizzed on that vocabulary right there, but it says what percent of the actual value is the absolute error? Well, we were off by 1,899 blue M&Ms. There actually was 1,984. When we make this division, if we multiply that by 100, then we will have our percentage, okay? So I'm going to put this in. 1899 divided by 1984 times 100. I get 95.7157258, but I'm just going to round this to the nearest tenth. I got 95.7% error. Now that is a lot of error, yeah, that's true. That's pretty far off, okay? But it's just an estimation. It's like, well, I mean, could you count how many? Sure, like, am I going to really, like, separate that many? No, I'm not. I wonder if this is supposed to say, like, how many M&Ms are in the jar, not just blue ones. It doesn't matter. It's just a demonstration to show how to find percent error. So, yeah, even though there could be a different number of blue M&Ms, and we don't know what the ratio is to blue to just M&Ms are, per serving or per ounce or anything like that, especially with the nutrition facts that we're given right there. But again, this is just to demonstrate how percent error is calculated. So the first thing that we did, right? You just find how far off you were, which is the absolute error. You divide that by however much there actually was, and then multiply that by 100. It changes it into a percent right away. All right, estimated in centimeters, the height of Charlie Brown. It says beagles, that's Snoopy, by the way, are 15 inches tall. How do we know that? I don't know that, but it was written on this. So we're going to say it's 15 inches tall. That's Snoopy, okay? So we're going to say, okay, Snoopy is 15 inches tall. How tall is Charlie Brown? So we're just estimating right now, okay? Someone give me a quick estimation on how tall we think Charlie Brown is in centimeters here. Now, it's just a percent error problem. So if we did estimate it at 300 centimeters, and some of you guys like, that seems unreasonable. It doesn't matter. We're just trying to figure out a percent error, right? Well, it didn't tell us, but I'm going to say it was 28 centimeters just because I can.
Wait. Why did we change inches?
200. No, it's 28. Yeah, because it's 15 inches for the beagle. Yeah, that's good. I take that back. We'll make it 28 inches right here, okay? So then I'm going to go on to Google and just see how tall 300 centimeters is. So 300 centimeters to inches. And it says it's 118.11. We'll just round it to 118 inches. Okay, so what is the absolute error? Well, we guessed 118 inches. It actually is 28 inches, we'll say, for old Charlie Brown. So we're going to subtract this. That'll tell us how far off we were. and that shows a 90 inches off. So what's the percent error? Well, we were off by 90. He's actually 28 inches tall, so we'll just multiply that by 100, the division. And that'll change it into percent for us. So 90 over 28 times 100. And we were off by 321.4. This is rounded percent. That's how much error we had right there. Okay? The absolute error is found by just taking the bigger of the two values and then subtracting the smaller of the two. No matter if your guess was bigger or if the actual amount was bigger. So you should never come up with a negative percent error, because error is just telling you how far off you were. It doesn't really specify if you were above or below. A police officer used a radar gun to clock a passing Ferrari at 131 miles per hour. That's MPH. The Ferrari was really speeding at 127 miles per hour. Calculate the absolute error. We're just going to figure out the percent error, by the way. So the absolute error, the police officer had the Ferrari going at 131. That's the bigger of the two. The smaller was really going 127. So we're going to subtract those, which means that I guess the speed gun or whatever was off by 4 miles per hour. So that's the absolute error, and it was over by 4 miles per hour. So we take those 4 miles per hour, we divide it by how much the Ferrari was actually speeding at. It was 127 miles per hour. We'll multiply that fraction by 100, and this will tell us the percent error on that. So 4 over 127 times 100. And I'm just rounding this to the nearest tenth of a percent. I got 3.1496 and some change. So 3.1% error. All right, two people, Reginald and Dwayne, measure their weight in the morning by using typical bathroom scales, instruments that are famously unreliable. The scale reports that Reginald weighs 237 pounds, though he actually weighs 256 pounds. Dwayne's scale reports his weight as 117 pounds, though he actually weighs 129 pounds. Whose measurement incurred the greatest absolute error? Well, let's start with old Reginald. Old Reggie. Nald. All right, so for Reginald, let's figure out his absolute error right here. So Reginald actually weighs, that's the bigger number for Reginald, is 256. Then we'll subtract the smaller number. That's how much the scale showed him at 237. So 256 minus 237, I got 19 pounds off. And we'll label this in pounds. And then in red, we'll do old Dwayne. So this is, the bigger number for Dwayne is 129 pounds. That's his actual weight there, 129. Then we'll subtract the scale value, 117. That's 12 pounds off. So who incurred the greater absolute error? Reginald did. Old Reggie. Nald. But who incurred the greater percent error? Well, let's do Reginald here first. So he was off by 19 pounds. To 19. He actually weighs 256. Then we'll multiply that by 100 to get the percent error. So 19 over 256 times 100. I got 7.4. That's rounded. 7.4% error. And then Dwayne was off by 12 pounds, but Dwayne actually weighs 129. And we'll still multiply that by 100 to get the percent error. So 12 over 129 times 100 equals, rounded, that's the 9.3%. So that's a 9.3% error, which means that if we were to base these results here, of course, Dwayne has the greater percent error. But since Dwayne weighs less, we could also make the assumption that the more you weigh, the less percent error you're going to get from this scale. Comparing percent errors. Sam performed an experiment to find how long it takes an apple to drop 2 meters. The theoretical value using physics formulas is 0.64 seconds. But Sam measured 0.62 seconds. So that would be how much time it actually took. 0.62 seconds. I mean, hundredth of a second, that's a pretty small 200ths. So the absolute error, well, the bigger of the two was the physics formula, 0.64 seconds. We'll subtract how long it actually took, 0.62, and so it was off by 0.02 seconds. So what is Sam's percent error? Well, he's off by 0.02. It actually took 0.62 seconds, so we'll multiply that by 100 to get the percent error. So 0.02
No, it actually took 0.
divided by 0.62.
Yeah, it's 0.64. Oh.
Yeah, 0.64 seconds is how long he thought it would take based on the formulas, whereas when he actually dropped an apple 2 meters to the ground, it actually took 0.62 seconds. So yeah, just, putting this in the calculator, divided by 0.62 times 100, I got 3.225-ish, so I'm going to round that to the nearest 10th, 3.2% error. Which means the formula itself was off by about 3.2% error. Of course, you'd have to do that many times to see if it's like a constant thing with the formula. So there we go. All right, so there's our formulas. This doesn't show the multiply by 100 afterwards, but you can put it there if you'd like. So big minus small divided by the actual amount. And yeah, big minus small, that's just how far off you were from the actual amount. Of course, if you had an absolute error of 0, so whatever you guessed was the actual amount, then you're off by 0, which is pretty easy calculation right there. All right, so that's our objective. Pretty much we're just using the formula. I can find the percent error.